welcome to this video on the topic of exponential functions. In this video, we're going to examine a phenomenon known as exponential decay. Now, exponential decay occurs in a situation where a quantity's total amount is successively decreasing by a percentage amount. Now, to get some context on this, we're going to have a look at a situation involving a fluorescent light bulb. More specifically, we're going to have a look at the power output coming from a 13 watt light bulb at the point at which it's been switched off. Now, when switched off, the light from the 13 watt bulb will decrease by 78% every second. Therefore, what we're going to see at t equals 0 seconds, the light is going to be at 13 watts. However, after 1 second has elapsed, what's going to occur is that the light itself is going to decrease or decay at a value of 0, 1 take, and it's going to be 78%, so 0.78, and that will be our watts. Now, computing this on a calculator, what we're going to find is that 1 second this will be our wattage coming out of the light. So what you'll notice is just before you go to bed, when you switch your lights off, if you have a light that's a fluorescent light bulb or something similar, there's always going to be this little afterglow coming from the light. So that's not your eyes, but rather it's light or residual power coming from the light bulb. And it's going to be going at about 2.86 watts in this case. Now, the light coming from this bulb is going to decay at a successive rate. So it's going to go, once we hit 2 seconds, another 78% is going to be wiped off the bulb. So we're going to go 13 multiplied by 1 take 0.78 squared. So you're going to multiply it by 0.78 once again. Putting this on a calculator, this will look like 13 times 1 minus 0.78, 1 minus 0.78, like so. Or you can just write it as squared, same answer. Following the trend, at 3 seconds it's going to decay even further. It's going to be cubed. So the pattern is, as the time goes on, the amount of decay is going to increase. Now, look in algebraic situation, at n, or at time equals n seconds, we're going to see a power output of 13 multiplied by 1 take 0.78 to the power of n watts. In the case that n is rather large, so if we go and we raise n to say something like 20 seconds, what you're going to see is it's basically 0. There's a value in there, but it's so close to 0 we wouldn't even be able to detect it with our eyes. So what we've got over here is a phenomenon known as exponential decay. Now, using this information over here, we can plot it and we can go a power versus time graph. Now, I've already gone ahead and I put this in here. Now, what you can see is our values on the left over here, so our time is put on our x-axis and the power output is put on our y-axis. So independent versus dependent. Or I should say dependent versus independent. Now, one thing you're going to notice from this graph is I haven't included any of the negative power region, so anything underneath the t-axis, and I don't have any negative values for t. This is because they're not relevant to the situation. In this situation here, we're not going to see negative power, or in other words, we're not going to see the light bulb generate its own power. And similarly, we're not going to see the time before the light bulb got switched off. So effectively, I'm only showing the relevant sections, so the sections we deduce information from. Now, using this graph, we're going to perform a few analyses. Now, part A of our analysis. Determine the values for A and B, and thus the mathematical model for the power discharge from the bulb. Or in other words, determine the equation P equals A multiplied by B to the power of T. So what values are we going to have in place of A and B to model this situation? P coming from the power output, T coming from the time. Now to do this, we're going to use a mixture of observing the information given in the question as well as pulling values from our graph. Now the first one we're going to look at is the multiplication factor, or the dilation factor. Now this guy can be deduced by looking at the initial value on our graph. The initial value being the first point at t equals 0. What we can see is it's got a value of 13. Now simply by inspection, when t is 0 over here, then it means the base is going to turn into 0, and then the only thing we have left, or the only factor, is a. So in our case, a has to be 13. Moving across, we look for b. b itself is going to be our base. So b is going to specify the rate at which we're decreasing. In our instance, we're going to pull it from the value shown over here. So 1 minus 0.78. Now putting all this together, we're going to get p is equal to 13 multiplied by 1 minus 0.78. So we're decreasing by 78%, all to the power t. And then we can simplify that down to p is 13 multiplied by, and then it will be 0.22 all to the power of t. So this is our mathematical model that describes the situation above. Okay, moving down. B. Deduce at what time the bulb is at 30% power. So what we're looking at is a situation whereby, going orange, we look for 30% power. So what is 30% power? Well, 13 or 30% of 13. The max power is going to be 13 multiplied by 0.3. Comes out to be 3.9. P 30%. Now what we're effectively looking for is when we're at 3.9% over here. So what value of t? Now to be able to deduce this, what we're going to do is use our calculators. So going up, we're going to go into menu, graph, then we're going to input the model that we found earlier. So 13 times 0.22 all to the power of, pretending this is t. Graphing and then setting up our B window. We're going to look between 0 and let's say 6 seconds. And then we're going to go for 0, and we have to go up to at least 13. So we just put in 13 here. We're not going to drop below a power rating of 0 watts. Okay, graphing. Here's our equation. Now what we're going to do to find what our time will be, so deduce the time, deduce at what time the bulb is at 30%. We're going to go to gsolve, xcal, and then we're going to put in 3.9 watts. Therefore what we find is that the bulb is going to be at 3.9 watts when it's operating at 0.795 seconds. So to solve this question, what we first do is we calculate the expected power output of what 30% would be. So expected power output, it was 3.9 watts. Then we simply model this inside of our calculators, and then we solve. We solve for the time when we're at 3.9 watts, shown over here. And this will give us the time at which we're at 30% power. Alright, moving down to C, deduce the power output at the end of the at the end of a 0.5 second blackout. So what's occurring here is the power might have failed for half a second. So what we want to do is we want to deduce what the power output will be after half a second. So in other words, we're going for, use green pen now. At half a second we're sitting here. Lots of arrows. So we want to know what this value is. Now by inspection it looks like it's going to be 6, but we don't really know that. We'll have to find out. So performing this, we're going to use our calculators, and we're going to go gsolve, tell me the value of y, and tell me the value of y when t is equal to half a second. and what we can see is it's not 6 but it's 6.097 or 6.098, and that's not going to be T, it's going to be so a nice simple one to finish with. So in summary, what we had a look at in this video was we had a look at the concept of exponential decay, that being when a quantity undergoes successive decreases in its total value by a percentage amount. Then we had a look at the scenario where we see the light from a light bulb decreasing at an exponential rate. So this fluorescent bulb, when you turn it off, the light itself is going to slowly decay over time. We then got the value, turned it into a graph, and then we turned the graph itself into the mathematical model shown over here, so the algebraic representation. After this, we answered 2 questions by some clever manipulation using our calculators.